Now let's get into our turbojet engine. If you're looking down here like this is just a gas generator, well, it more or less is. All we've got on here is a nozzle and, a diffuser and a nozzle. There we go. Said it the right way that time. So diffuser and a nozzle. And then we have a very, very basic turbojet engine. We can do other modifications later on to turn into different types of turbojet engines. So we're going to look at each of these components in turn. We're going to focus on this inlet to start. As you can see, I put that picture up here, so as we go through these next several sections, you'll be able to see how we've progressed through our gas generator engine. Okay, so what is the purpose of an inlet? Well, an inlet is all about decelerating our flow, okay? And we're doing that because we want to get it down to the Mach number that our compressor actually functions at, which is typically around 0.5 to 0.6. So we got to slow down that flow. Now, if we were in a perfect world, this would be an isentropic process. However, while it is adiabatic, okay, that's because we have a very small temperature gradient across this wall, it's not reversible. Now, this is due to several things. One, usually an adverse pressure gradient, that's what's slowing it down, and that causes separation. So if we're on that wall right there, still using that picture up here, it's more than I expected. It's going to have some separation right here. Now, we can get rid of that if you tailor your geometry of your inlet properly for your particular Mach number. You can actually make it stay attached. Though as you get to faster and faster Mach numbers, like higher and higher above 0.5 and 0.6, this gets worse and worse and more difficult. Now, for supersonic aircraft, there's a much more obvious problem, which is simply that there are shock waves. Okay, you have a shock wave that's already making it irreversible just to begin with. But if we're subsonic, then it's mostly just it's going to separate. That boundary layer separation is our biggest problem. Okay, so here's my HS diagram for an inlet, and while there's a lot going on here, I want to explain it as best we can. So let's focus in. So first off, the max amount of energy conversion possible from kinetic to enthalpy is right here. So if I were to go all the way from whatever my velocity is to 0, that would be the max amount of energy I could put into my enthalpy. Now, I don't want to go to 0 velocity. So no matter what, I'm going to have some kinetic energy that remains unconverted because when it reaches the compressor, it still has a velocity. We said like Mach 0.5 to 0.6. So not all of it gets converted. Now, no matter how hard we try, this is not an isentropic process. While this is somewhat exaggerated, but it's still not an isentropic process. It's irreversible due to friction and separation. So we're going to have that entropy increase. And because we have this irreversibility, we're going to have a loss in total pressure. And where does that energy go? It goes from being useful, I can use it to produce work, which is what I want to do my turbine, to just being hot. Okay, it just got hotter, which we don't like because we don't want to have extra heat because it's just going to make things melt. And so we're going to have to do more cooling because of that. So this is my overall diagram right here for what you can see. This is the max we can convert. We don't convert all of it. We have some entropy generated, and that leads to a loss in total pressure. Okay, so now let's use this to figure out how efficiently our inlet is working, okay? How efficiently is our inlet accomplishing its deceleration? So, like we know, we realize that if it was isentropic, it would take a lot less kinetic energy conversion to reach the same final state. Now, we have to convert the energy no matter what because we have to slow it down. But just getting to that same total pressure, that same enthalpy we actually end up at, it would have taken less if we had been doing this isentropically. So here's the two differences. This is the ideal scenario, how much enthalpy change it takes to get to that particular state I care about. And here's how much enthalpy conversion it actually took, okay? It took more. It took more energy to get to the same state. And I never like to do that. I don't want to take more energy to get to the same state. So this is my ideal case. That's the difference between a imaginary isentropic state 2 for total enthalpy. And then I have my real enthalpy at state 2. My real total enthalpy at state 2. And that's being compared to my enthalpy before anything happened. Now, we realize that irreversibility is going to reduce my total pressure. And if you think back to thermodynamics, you can see how that's going to come into play. So my total pressure loss, my total pressure drop is a function of my entropy generation. The more entropy I generate, the smaller that ratio gets. And the worse off I am, the less flow work I have to smack into my turbine and actually keep me flying in the air. So we don't want to waste this, because if I am wasting that energy, I have to put in more fuel and burn more fuel to add it back. So let's not waste it. Okay. So now we have two terms that are kind of important for us. We have the diffuser efficiency and our total pressure recovery. That's saying how much of my total pressure is still there after this inlet. And guess what? They're related. Okay, so here is my basic equation for how my total pressure and static pressure are related as a function of Mach number. You saw this in Euro 2 so far. Hopefully you're familiar with it. Now let's do it again, but this is now for after the inlet. And you see that it looks really, really similar. The only difference here is I've added in this one term, which is simply saying that is my diffuser efficiency. Okay, that's my diffuser efficiency. And it's simply saying that I'm not doing this isentropically. This is isentropic, this one is not, and that term tells me how far off I am from being isentropic. Now we can use our chain rule to connect my diffuser efficiency to my total pressure recovery. Because that total pressure recovery is simply the ratio of my total pressure after the inlet and my total pressure before the inlet. And so you can then see, like, wait a second, chain roll that out. Well, here's this guy, and this is just the inverse of this one. And so I can put those two together. And it is not by any means a very pretty equation, but you can see it's simply the ratio of what the ratio, it's a ratio of ratios. This is what my total pressure to static pressure ratio would have been, and this is what it actually is. Okay. Oh, went too far. So we're going to stop here, and next time we will do an example problem. So tune in next time. I'll see y'all then. Have a good one. Bye-bye.